Hey there, I'm Brett,
I'm Umar.
and we're Brett Newmar Incorporated, coming to you live with the all-new and prototype PlantBot. So, a little bit about the PlantBot.
We were thinking about what we wanted in our robot project, and every morning I'm a little cold, and I joked around about how I needed to photosynthesize outside of HBAR for a little bit, and
so we were looking around trying to figure out what sensors we were going to use, what our robot was going to do, and we came up with this idea of like finding the best spot for a plant because we just like to photosynthesize in the morning and warm up. Hey, we're back. So we just want to talk to you a little bit about what our photobot does. Well, what it does, Umar?
it will go to greater light sources, and once it gets to that greater light source, it'll stop there and check out how much carbon dioxide is at that level, and then give us a reading about how great that spot was.
Starting. Oh, hey, PlantBot, finding a home, eh? Oh, looks like you found your little home. Is that a good spot?
Now that we have tons of light going onto our photobot, we have currently
Three LEDs
lit up. And now with the carbon dioxide source added, courtesy of Brett Young,
I play trombone. I know how to blow carbon dioxide.
and there we have it. We have 5 LEDs lit up, indicating an optimal plant environment. So when we talk about our circuit, first of all, we need to look at how the majority of our circuit simply reads voltage values. It looks at our solar panels, grabs the voltage, and compares it to the other solar panel. It looks at the voltage difference across our carbon dioxide detector, and we'll read that value. But when we're not reading voltage values with our circuit board, we're looking at an astable circuit that utilizes a 555 integrated circuit from the MIMS textbook. And we added a little something special, something novel, to make this work for our intents and purposes. I'm going to talk about the novel stuff later maybe, but
Go.
Yeah. So when we look at the astable circuit, here's the 555 integrated circuit, and we use 2 resistors and a capacitor to regulate the time constant, how often our integrated circuit gives like a positive or negative value. So when we look over here, that'll correlate to something being on or off, which in reality ends up being something like 3.4 volts versus 3.2 volts. But the point is that we will be regulating when something is red or not red. And in our case, it ends up being about half a second between an on LED or an off LED.
Hey, Umar, so I got a question for you. Well, what makes our circuit novel?
Great question, Brett. This is where the magic happens. Right around here, when we're sending in the on or off value from our integrated 555 circuit, that's how often our LabVIEW code is going to evaluate our score. That's how often it's going to recognize that the score is either a 2 or a 4 or a 5 or a 6. Based on how high that score is, then after every reading, every on and off, it'll light up either 1 or 2, 3, 4, to up to 5 LEDs representing our score.
So a little close-up on the circuitry. Well, let's first start out with our solar panels. These are our solar panels that are detecting the light and deciding which way the robot's going to go. If we move on to the next thing down the line, we have our LED, our row of LEDs. Now, you might wonder why there's a little cardboard around it. Well, we were noticing that, you might have noticed earlier in the video, they blink. So, of course, they would affect that right solar panel, and yeah, they did. So we had to cover up the light getting emitted. Let's move on down. We got a couple wires right here that are giving our LEDs power, controlling. So we, right here, have our CO2 detector. It is controlled, I believe this one right here. Oh yeah. This wire right here is the power. Here's the ground. And here's where we're reading our voltages off. And here's a capacitor. our 555 timer, and our 2 resistors in series, yeah. And all these red wires that you see running down right here are all headed into the lab jack. And there's basically what are giving us our voltages. There's one of them in our voltage source powering our whole system, but all the rest of them are in DAC 0, DAC 1, analog in 2, 3. There's some on the other side. We basically used every single one. Right here is the power to our circuit. Top side of our circuit, and here's the ground, bottom. Yeah, it's in the beautiful Bensky. If you would dress your attention, there's a what's that, Bensky? There's a compass on our circuit board. I would like to address that. Look at these straight, beautiful lines, no crossing.
Go. So first, with our LabVIEW code, we're just going to be reading out our graphs here. That's just about all that's going on here, the graphs. Now for the bulk of our LabVIEW code. Here's where we open up our LabJack and we'll start reading in values. We'll read in easy analog input 0 and 1, which correspond to solar panel 1, solar panel 0. One of the problems that we experienced was that one of our solar panels constantly read out very small voltages. So we had this little value to adjust for that difference so that we could really see which ones were getting equal. We could see when they got equal amounts of light. We dealt with that calibration issue with that addition of 0.05. We also are going to be paying attention to the difference between these two values, as this is key in when our program stops. When the difference between the two light intensities from the solar panels are close to 0 or less than 1, we'll register it as true. Now that we've registered which one is greater, the program will either move true, which is right, or false, which is left. Now, while it's moving false, it's going to be moving forward, and then if the value up here, the difference between them is close to 0, this case structure will read true, stopping our motors. Now for the scoring. This is the part of the code that decides exactly how good our environment is. We'll read our CO2 level here, and we brought over our solar cell power over here and divided them by the max value that they could have. By doing that, we'll get a number like 1 up to 1, or up to 1 over here, add them together getting possibly 2. Multiplying that by 5 and you'll get an easy, simple score out of 10. That should be it. This is the part where we look at our 555 timer readings and how many LEDs we're going to light up as true. So if our 555 timer is going to give us a voltage value above a certain threshold, which is above, at least on, then we'll enter this case structure as true and light up however many LEDs we need compared to our score. If it's greater than 2, 1 LED is lit up. Greater than 4, 2 LEDs are lit up, and etc. If the case structure was false, we're going to turn all the LEDs off. That way we have blinking of all of our LEDs for however many LEDs we need to represent our score properly. Now we're going to show how the graphs change based on the values that we're measuring. Notice the solar cells are getting their voltages, both of them having their different voltages because they're off by a certain amount. And the CO2 graph is around 1.1. That's kind of the standard for this room environment. But now that Brett's going to change some of the variables like light intensity or CO2. Come on, give it some more CO2 than that. We can start seeing the CO2 rising, getting up to its maximum of 4. That's the max our CO2 detector can even give us in the first place. And we can see how the light intensity is changing as Brett's shadow gets over it. It's going to turn on a lamp, show it really going up. Oh, there it is. Solar Zero's graph goes up quite a bit.